Okay, good afternoon to all of you. We shall continue from this slide. We have stopped at on Monday, right? We talk about data representation, right? What is a byte? We know that by combining 8 bits together, it will form a single byte. But because of 8 bits, you will be able to produce 2 to the power of 8. That is 256 different patterns. With 256 patterns, we have enough patterns to represent all the alphabet, numbers, and special characters. Right, and with that, we will be able to come out with a coding system. There are a number of coding systems in the next few slides. Okay, first, in this slide, we see the example here. Right, the first one here is a byte of data, 0011, 0011. Okay, so 8 bits. Last lecture, some students asked me about this one. Why do I get a 33H? The 33H is in hexadecimal. So what you need to do is get a byte divided into 2 parts. For each 4 bits, you form a hex number. Because with 4 bits, you can go from 0 to 15. Right? Hexadecimal will run from 0 to 9, followed with A, B, C, D, E, F. So there are 16 patterns. Right? So with this 0011 is a 3 hexadecimal, another 0011 is a hexadecimal. So we have 33H. And how do I come up with the number 3 for this representation is you have to go to the ASCII table. I think the next 2 slides will be the ASCII table I showed here. Right. If you look at any ASCII table, you will be able to find out the code for the particular character. Right. Just now we talked about 33, right, hex. So how you look up for 33? On the column here, we can see that 30 means this row starts with 3. And then for each column here, you have the number. For 30 and add 3, we'll have a 33 hex. And I get a number 3 here. If I get 30 and 5, I will get a 5 there. Right, if I get 40 and 4, I will get a capital letter D. Right. So that is exactly the case of what we have seen here. 35, you find a character 5. And 44 hex, you get a character capital D. Right. This is how you come about with this number. Of course, I will not ask you to look up for this number in a quiz. Okay, there's no one that can represent the ASCII table. Right. But you have to know that in order to find out what characters, you have to look up in the ASCII table. Right. Okay, we mentioned about coding system. Why is there a need to have a coding system? Basically because it will make it possible for human beings to communicate with the machine, a computer, right? You need to have a language. So what we need to do is we use a coding system, and we will be able to input data, say text, characters, or even image, audio, or video. All these will go into the binary number, right? So for every byte, you know there are 8 bits that represent certain characters or represent certain image or sound, right? And coding standard also make it possible for different kind of computers to work together. Different devices, computing engine will be able to understand each other if they understand the same coding system. And over the years, in fact, different coding systems came out, right? Just how we mentioned about ASCII, it's just one of them, and there's another one very famous, EE8092. This one mainly from the IBM mainframe initially, right? You can see that for symbol 0, 1, 2, 3, under the ASCII, remember just now it's 30 will be for 0. However, for EE8092, it's different. It's 1111, 000. So if you have one system talking about EE8092, need to communicate with another system talking ASCII, then you need to do a conversion, right? So only those big ASCII will be able to communicate directly, right? So as I mentioned, we have up to a number of coding systems. The 3 famous ones are here. The first one is ASCII, stand for what? American Standard Code for Information Exchange, right? And the other one is EE8092, right? I think the short form for this, Extended Binary Coded Decimal Interchange Code. And of course, with more countries, different languages join into the computing engine. computer system, we need to have a coding system that cover all the international languages. So the Unicode come into picture because there are so many characters, especially Chinese, Japanese, and Korean, right? They have many, many different alphabets than ABC, right? So they need to use a 16-bit system. With 16-bit coding, we can come out with 2 to the power of 16, which is 65536 number of characters. So with this Unicode, it does help to come out with a representation for all the characters. Maybe we take a look at an example for Unicode, right? You can see that for each one, there is a 4 hex number. At the bottom, for each character, you have 4 hex number. Every hex number is 4 bits. So 4 times 4 give you a 16-bit coding system, right? And this is Chinese, this is Korean, and that is Japanese, right? So all the different characters to be represented. This is just part of it, right? If you want to have the full characters range, you have to go to internet to look for that. Okay, next. This is just an ASCII table. I think you have that in your note. Okay. Just how I mentioned, in order to look up the code for, say, I want to get 7. What is the code? You look for 30 here plus 7. So 37 hexadecimal is the number 7. Okay. Right. That's sum up about the data representation, and we move on to another important topics about memory. I think I'll spend almost all the time on this topic today, right? Memory. That memory will consist of what? Electronic components that store what? Store the instruction that you are going to execute, right? And also store the data, the one that you are going to process. You know the computer will take in the raw data, subject it to the instruction, and then produce a result. Process it and produce a result. So the result being processed is the information, right? All this will be stored in the memory. You need a memory for this purpose. And basically, you store 3 basic categories, 3 important categories. That means all these are classified under. First group is the operating system and the what? And the other system software. Will be all housed inside when the computer is running, it will store in the memory. And also application program, those that you want to run, like the browsers, like the word processor, right? And also the data being processed, and also the result, right? When you process data, it becomes information, which is the output. Right, another concept, what is an address, okay? For every byte of data in the memory, we need to have a location to locate it. Just like all the houses in Singapore will have a unique address. Okay, in order for the postman to deliver a letter, you need to know the unique address. If you have no unique address, then the letter can go to 2 houses, any one of them, right? So for every memory location, we need to have an address. It's just to pinpoint to a particular byte of memory the particular byte in the memory. Okay. And for PC, we are talking about the address, only address a single byte, okay? No matter whether you have an 8-bit, 16-bit, 32-bit, up to now I think the PC is a 64-bit machine. However, the memory is still organized as a single byte per location. You are just looking at every address, there should be a single byte, okay? So we call it a byte addressable memory system. Every address will only house a single byte. Whether you have a 64-bit or 32-bit, every location is a single byte, okay? And of course, the more money you have, you can buy bigger memory for your PC, right, or your Mac. Memory size is measured in what? In this term here. In the older days, we talk about kilobyte, okay? KB, that means 1024, right? And then we have megabyte, MB. Remember, all the B here are capital, right, for byte. Gigabyte, and then also terabyte. Basically, the TB here is more for what? More for hard disk. At the moment, the RAM or DRAM, we normally talk about GB, not so much about TB, right? So the table below here will give you a more detail about each one. For each term here, how big is the size of that means the number of bytes of memory that you have. For kilobytes, it's based on, remember we are talking about binary, so the exact figure has to be based on 2, right? So for kilobyte is 2 to the power of 10. That is 1024. So for quizzes, for exam or whatever, we will always want to be the exact number. You might see the newspaper come out with say 1K is equal to 1000, but to be exact, for 1K in this binary system is 1024. We will always rely on 2 to the power, right? So megabyte is 2 to the power of 20. This is the exact amount, right? You cannot just simply say we have about 1 million. The million itself is not an exact figure, right? So I think the rest are the same. The GB, gigabyte, 2 to the power of 30. So the equivalent will be 10 to the power of 9, right? So the other last column here give you approximation of number of pages. When we talk about a page of text, basically it's like A4 size. How many bytes will that would you need to represent this page of text? It says one page, in the past we normally talk about 80 columns and about 25 lines, okay? So 25 times 80 give you about 2000. 2000 bytes, because every character needs a single byte to represent. So a page of text will be about 2 kilobytes. That's why based on here, a kilobyte will be able to store about half a page. So if you have 1 megabyte, then it will be about 500 pages, right? Same thing. So this table roughly gives you the size of memory needed for the number of pages of text. Right, we go into the different types of, 2 basic types of memory, okay? The system now we have 2 types. First one is based on whether the data can stay when the power is off. The term here is volatile or non-volatile, right? Volatile means it's temporary. So for this kind of memory, it loses its content when the power is switched off. So the moment you off your PC, you know your DRAM content is gone, okay? And the other type is the non-volatile, or we call it a permanent storage, right? When you power off, the memory content still stays, right? And good example for the volatile one is a RAM or DRAM or SRAM. Doesn't matter, it's just a RAM, random access memory. For the other one is a ROM, read-only memory, or the so-called flash memory, the one that you store your music, your photo in a thumb drive, right? Or your just a memory card. The other term CMOS is a little bit controversial here, because CMOS talking about actually is to be volatile, but for most of the computer, when you talk about CMOS, is storing the basic setting of the PC. And normally there is a backup battery next to the CMOS. So even when you power off your PC, the backup battery should be able to hold the content of this CMOS. So strictly speaking, it shouldn't be, it should be classified as volatile as well, but I think there is a backup battery there, right? So more or less the data still stay, right? I think many of your devices, like digital camera, might have certain CMOS inside as well, to keep the date, some other information, even when you you are doing the changing of battery. All right, we move on to the term here, the RAM. Okay, RAM stands for Random Access Memory. So when you talk about random, what do you mean by random? That means because there are so many different locations within the RAM chip, right? The random means you will be able to access the content with equal access time, no matter where it is located. Right, you should be able to get about the same access time, no matter which location. Compared to it is the sequential access. Many of you who still play with the videotape, you know sequential access, it depends on where is the content you want to look for. So assuming the particular video is toward the end of the tape, you know that it will take a long time to get the content. So that is called a sequential access. For computer, when we talk about sequential access, basically we refer to tape, magnetic tape storage. For the other kind of storages, most of them are random access. But we talk about RAM first, it is a random access, right? It said memory chips that can be read and written, That means both directions. You can write data into it, you also can read the data from that. So that is called the RAM. And Also call them main memory or so-called primary storage. Okay, remember all these terms are equivalent. Main memory, or we call it primary storage. And most RAM is considered volatile. That means when you switch off the power, the content is gone. So you have to make sure that if you want to keep it, you need to write it back to the hard disk, right? Before you shut down the system will back up in the hard disk. He said the more RAM is in the computer, the faster the machine. This one is an open question. So think about that. Why the more RAM you have? Why normally when you have 1 gigabyte, then after a while you find that your computer getting slower and slower, or you feel that it's slower and slower, you go down to the system there and buy additional RAM to make sure that your computer runs faster. Why the more RAM the merrier, right? Why can it run faster, right? Find out the reason. Okay, next we talk about 3 basic types of RAM. Okay, there are three types here. The first one is a DRAM. The second one is a SRAM, static RAM. The first one is called dynamic RAM. And the last one, very uncommon, most of you never use it, magnetoresistive, right? They call it an MRAM. Okay, we spend more time on the DRAM and SRAM, okay? We will not just go into detail about this one because basically at the moment it's still very new, not really available in the market. Very few people have a chance to use it. They are newer, using magnetic effect. And that means also non-volatile in the sense the content will be able to stay because it's magnetic, right? So when you switch off the power, the content still there. And good thing about that is access time is about the same as the other two, right? Can match up with the performance. For DRAM, you need to be re-energized. Later I'll touch on why it needs to be re-energized. And typically it's used for your normal needs like storing instructions, storing data, information when the computer is doing the computation, right? Just how I mentioned, the more the better, right? And for the SRAM, it's basically it's a lot faster than DRAM. I'll also mention later why it's faster and also more reliable, more expensive. When you have things which is faster and reliable means more expensive. And you cannot afford to have too many. You do not talk about gigabyte of SRAM in your system. You talk about megabyte maybe, not gigabyte. For DRAM, you talk about gigabyte, right? You can have up to 8 gigabyte at the moment. I think many of you get a computer with 8 gig in a notebook, right? Okay, there are other terms for DRAM as well. There are all these variations. I might have a bigger picture. Yeah, this is the one. Okay, we go into the different name for the DRAM family. First one is SRAM. Okay, S stands for synchronous, right? Synchronous DRAM. Is it synchronous to what? Synchronous to the system clock. So when you have a faster clock, the transfer rate will be higher, right? The transfer speed or access time will be much higher. It says it's much faster than the traditional DRAM. Next is DDR. DDR stands for what? Double data rate. That means you know that it's 2 times. For each clock, the data, means the RAM will be able to transfer 2 bytes. Okay, so that is 2 times the speed. And then we have DDR2, so second generation of DDR. DDR3, third generation. Every time when you change the generation, you expect the transfer rate or so-called the access time to transfer time. The access time will reduce, transfer rate will be improved, right? And the last type is a special type called the RDRAM, which is RAM bus. It's a special bus that makes use of what? Pipelining. We heard about pipelining, right? So it will be able to achieve certain degree of parallelism so that it can improve the transfer rate. Right, we look at the modules. Right, when we talk about the memory inside the system unit, we talk about the memory module. We do not buy a single IC, right? The IC will be prefabricated on the PCB, a small PCB called the memory modules, right? He said, where does the memory IC reside? First, it is attached to a small circuit board. Remember, a small circuit board, all the components will be attached to that circuit board. This is a picture here. We have a small circuit board which have some connector at the edge. And then all the different memory chips, each one is a single chip. Right, each one will provide a single bit. Remember, every byte will have up to 8 bits, right? So you need to have at least 1, 2, 3, 4, 5, 6, 7, 8. 8 bits is minimum. And sometimes you have 9. Next few slides we'll talk about why we need to have 9 IC here, 9 memory chips. Okay, in order for this to be connected to the motherboard, on the motherboard you should have the so-called memory slot. Okay, the memory slots are always there, and typically they will provide 4, right? 4 slots there. So if you buy 1 gig per module, you can put 4 gigs in maximum, right? However, when you buy a new computer, when the vendors try to sell you, say if you want to have 4 gig, and they give you 4 modules, do not accept that. Maybe you try to get 2 times 2, so at least you have 2 spare slots, right? So that is to cater for future expansion. You want to have more memory, you still have 2 more slots. If you occupy all the 4 slots, like for example 4 times 1, all the 4 slots are used up. When you need to upgrade to increase to 8, you have to throw away all the 4 because nobody will buy maybe they will just trade in with a small amount of money. So try to leave certain empty slots. This is just from experience, right? Okay, typically when 4 times 1 it will be cheaper than 2 times 2, okay? Because they know that 2 times 2 is more in demand, right? Of course now you're talking about 8, right? So it must be 4 times 2 or 2 times 4, right? Okay, so just now I mentioned about 8 chips is minimum to make up 1 byte, right? And 9 chip is for parity check. Okay, we'll talk about parity check next. First, we look at the different modules. They have a name for all these different memory modules. We have this, the MM here stands for memory modules. We have SIMM, DIMM, SODIMM, and RIMM. We will go through the 4 main types. First, SIMM, right? It says for these modules, the pins are on the opposite side. Normally, the module will have pins on both sides. It said the pins on both sides are actually physically connected together. That means for each pair, it's equivalent to only 1. So in this case, this is all single in line. Basically, you only have 1 set of pins. Okay, whether you have contact on one side and the other side, they are the same contact. Okay, they are connected together. The opposite of that is DIMM, dual inline memory module. In this case, they are all together 168 pins, quite a number of that, on opposite sides of the circuit board. However, they are not connected together. That means each side will give you half of that, right? 168 divided by 2. So the 2 sides add up together 168 pins for you to slot into the memory modules, so-called the connector, right, on the motherboard. The third one is a so-called SO, right, small outline. Small outline basically is the same as the DIMM, except this is mainly to be used for what? For notebook computer. Because you know the notebook, the space is a premium, right? You want to have smaller size so that it will not occupy so much space. So this particular module, the small outline, is catered for the notebook computer. They have 144 pins, not the one just now was 168, right? Okay, so mainly used for notebook. And the last one just now we talk about RAM bus, right? RAM bus inline memory modules. So this is typically using the RDRAM. Okay, the components on the module is the RDRAM, and this is typically quite similar to DIMM, except they make use of a RAM bus, a very special kind of bus that get a higher speed. Just now we mentioned using what? Using pipelining. However, I think it's not popular. Nowadays, you seldom heard about RAM bus, okay? You do not talk about RIMM. Most likely, it's still the other more standard, okay? This is a very special case. Right, next we talk about refreshing DRAM. Just now we talk about DRAM need to be refreshed constantly, otherwise the content will be missing, right? After a while, if you do not refresh it, the content will just disappear. Why is that so? Is that this refresh operation is where the dynamic RAM. Why we call it dynamic? Because you need to refresh it constantly. And you are not talking about every 1 second or what. Every millisecond or nanosecond you have to do a refreshing, right? And DRAM has to be refreshed because you forget what it's holding, right? And he said the downside of this refreshing is what? Since you need to do it so often, the speed, the performance drop compared to SRAM, okay? Because you need to visit every location to do a recharge. I mean, it's not you, but the system has to do it. The reason being that I'll just show you this diagram, okay? Not so much technical, because it's basically for EE students, but roughly we know the internal working principle. For DRAM, they want to have high density. So basically, there's only a single transistor that decides whether the bit is a 1 or 0, right? A single transistor will be able to do that. So more bits can be packed into the same area, right? So it's much denser than the SRAM. That's why DRAM is cheaper, because with this single transistor is considered 1 bit. However, in order to make a SRAM, the SRAM will need to have 6 transistors to build up a single bit. So definitely in terms of density, it is at least 6 times lower, right? So however, with the 6 transistor, that system will not need to be refreshed. For this one, because a single transistor, whatever charge stored there, assuming that's it, if there are charge on this transistor, we consider 1, and if there's no charge, we consider 0. This charge will disappear over time. It will not stay forever. So when we talk about refreshing, we have to visit every single transistor here. If we see a 1, we will charge it again. If we see a 0, we just leave it. Okay, so the location, the information at that location will always be refreshed. However, this takes time. Okay, but good thing about that is higher density, cheaper. Okay, that's good thing about that. So we know about why we need to refresh DRAM, and the term dynamic means we need to refresh it. Of course, it's the computer circuitry that do the refresh behind the scene. However, even behind the scene, the computer takes certain time to do this job, right? Any additional job count, right? Right, next is, just now we talked about parity checking, right? We said we need to have 1 additional, for those modules that has 9 IC, one of the IC will be in charge of the parity checking, right? He said there are 2 types. We call it odd parity and even parity. Let's take a look at the odd parity. Assuming you have a byte to be stored at a location, and that contains an even number of 1. Even number means 2, 4, 6, 8, right? For this case here, can you see that there are 2 1? The number in red are the actual byte to be stored in the 8 chips, memory chips, right? So we have 2 bits over there. It's an even number. We will make 1 for the parity bit. So that make it odd parity. So for this number here, we have 3, right? It's an odd number. We will put a 0. So that means including the parity bit, the total number of 1 must be odd in order to call an odd parity. For the even parity, just the opposite. If the content includes the even number of 1, then we will put a 0. So the total number of 1 should be an even number. Same thing here. This one we have 3, so we add 1 here. 4 ones is an even parity, right? So odd parity and even parity for error checking. Okay, next we talk about so-called ECC. Sometimes you heard about this name, ECC memory. ECC stands for error control coding, right? Or so-called error correction code. Sorry, not control, correction code, right? It's a high-end server usually cannot afford to have the data corruption, right? The memory system that are used inside the server, typically we will have ECC built in, right? So if there is a single chip, single bit error, the system will be able to do error correction. That means whatever single bit error will be corrected. However, if there are more than 1 bit, they can only detect it, but it will not be able to correct it. So if there are more than 1 bit having having error in the single byte, that whole byte should be disregarded. That means you cannot get it recovered. Okay, that particular information is considered corrupted, right? But a single bit, they will be able to correct it. That's called a single bit ECC. Okay, next we move on to another group, the static RAM. Okay, static RAM is important because we want to talk about cache memory, right? A big topic on this. The SRAM or static RAM typically used for cache memory, and which is very fast and also reliable because these chips do not need to be recharged. Just now we talked about DRAM need to be refreshed because there is a single transistor, right? For this SRAM, because there are 8 transistors, like the diagram here, so we will not need to refresh it constantly. So in terms of circuit performance, it will be much faster and more reliable because you do not have to worry the charge dissipate away, right? And DRAM chips, means for this case, we call it static because we need not to do the refresh constantly. So we call it a static RAM. And they are more expensive than the DRAM. Okay, next we talk about the cache memory help to speed up. Why do we need to have cache memory? Because it does help you to speed up the computation. It says that cache memory will store the frequently used data. Cache memory itself is faster. When you talk about access time, for example, you need to move a byte from DRAM, it might take somewhere around 15 nanoseconds, okay, to move it into the CPU. However, for static RAM, we are talking about maybe 5 nanoseconds, maybe 10 times faster than the DRAM. The 2 is about 10 times better, right? The SRAM will be able to do it 10 times faster, right? So if we keep those commonly used data or instruction in the SRAM, we will be able to get the data faster, right? Because whenever you can look for that, it's there, so you can get it in, right? It said when the processor needs to get an instruction or data, it will go through this search sequence to find it whether is it inside here. If it's there, I'll do it. I'll get it from there. So the sequence is like that. If CPU needs to read certain data or instruction, first you look for level 1 cache. Later we will talk about L1, L2. Okay, L1 means level 1 cache, a small quantity only. Like this case, we have 16 kilobytes. If we cannot find in level 1, you go down to level 2. Level 2 will have slightly bigger quantity. And only when you cannot find in the cache system involve L1 and L2. But if you cannot locate it inside here, means you have to go down to the main memory. And main memory, you are talking about 10 times slower, right? So that slows down the process. So as fast as it can, you try to look up inside the cache system, right? So you know that this small amount of memory is important to help you to speed up the performance, right? Okay, for personal computer, typically you have 2 or up to 3 levels of cache. Okay, you have L1, level 1 cache, L2 and L3 in fact. Okay, for L1, typically small quantity from 8 kilobytes to 128, depend on the system, right? If you have more money, high-end machine, you have more of L1. And L2, typically from 64K to 4 megabytes. Okay, remember L1 are of better access time, and L2 will be slower. Okay, although they are all SRAM, but SRAM also have different grades. Some are faster, some are slower. So you can typically say that L1 is a lot faster than L2. L2 is a lot faster than typical DRAM. Okay, so this go from this to this, and we can always say that if let's say L1 having 8K, then L2 should be around 64K. L2 is always more than L1. You don't say that the L1 is having 128 and L2 equal to 64. Nobody designed such a system because both L1 and L2 have a range, right? So if you have L1 equal to 128, you expect the L2 to be around 4 megabytes. Okay, in a few times higher than L1. Okay, and there is also another type called the ATC, Advanced Transfer Cache, which is a version of L2 cache. This L1 and L2 are typically housed inside within the processor itself, okay, not external. And it says ATC will allow the L2 cache to put inside the processor chip. That means the whole cache system is part of the processor, put inside the processor chip itself. And it is a lot faster because inside they have a 256-bit wide system bus. Right. So just now we mentioned about L3. Typically in the past, L3 is the cache that do not house inside the processor. Just now I mentioned L1 and L2 or L2 ATC, right? All the L1, L2 are part of the processor chip. The L3 level 3 cache will be the additional cache system that you put on the motherboard itself, external to the processor, right? However, that might not be always true because with the newer microprocessor, because they have a lot of transistor built in, they can afford to also put L3 cache inside the processor. One typical example is what? Intel Core i7, okay? Remember, let me see, is it this one? Okay, this is the Intel Core i7. If you take a look, there is a shared L3 cache, right? Each core here have their own L1 and L2. Everyone, there are 4 cores, right? Each core will have their own L1, L2. Together, they can have enough space to squeeze in a shared L3 cache, okay? So, for i7, in fact, what I mentioned just now, the L3 is housed on the motherboard, external to the processor is not valid, okay? Only for this case, right? For more advanced processor, the L3 might be built into the processor itself. So one way to look at this 3 level is we have the L1 cache, part of the processor, L2 cache, also part of the processor, right? And then if you have, I mean this is the older low-end system where we do not have the things like i7, right? So you have L3 external to the processor that is built onto the motherboard, okay? You have additional module or additional chip to build into the motherboard. And of course, the next will be the RAM, okay? If you cannot find in L1, look for L2. Cannot find in L2, look for L3 if there's L3. If not, then you have to go down to the actual DRAM, okay? The main memory area to look for the data. So in terms of access time, this is also the order to look for, right? Okay. Right, let's cover the DRAM and SRAM, okay? Another type of memory is just how we mentioned, the read-only memory, ROM, right? Read-only memory. And what is read-only memory? It says that it's the memory chip that stores permanent data or instruction, right? Permanently because even when power is off, you do not want to lose the data or instruction inside the memory. This is so-called the ROM, read-only memory. And they are non-volatile and basically the content stays right after the power off. We want to further classify them into 3 groups, 3 types. First one is the ROM, read-only, the typical read-only memory. This is also called the mass programmable. Mass means the IC manufacturing process. Remember, if you heard about how the IC is being manufactured, they need to have many different layers of mask, right? Then they shine the lights onto it to etch the circuit. So this is mass programmable, means the content is decided during the process, during the IC manufacturing process. So we call it a mass programmable. That means the content is decided at the IC factory. And it cannot be changed. Once it's programmed, it's already built into the component, you cannot change it. Right. The next group is called the PROM, Programmable Read-Only Memory. These are basically blank ROM, okay? That means the content is not programmed. The programmer, whoever buys it, will be able to program on the spot, okay? You buy something to program yourself, okay? It's not decided at the factory, okay? They give you a blank chip, and you have a way to program it. And we call it field programmable. Field means at your site, right? the place where you say, for example, you are going to design some microcontroller based system. Say, for example, micro mouse, very famous for poly and JC students, right? Micro mouse typically will have a microcontroller or a processor, right? And they will need to have a program to decide, to guide the micro mouse movement, right? So that content is, the program is normally housed inside a PROM, okay? More likely to be the next one, sorry. This one, because the content can only be programmed once. Basically, the field programmable means when you do the programming, you are burning certain fields inside this chip. By applying a certain voltage, the fuse will blow or stay, right? Depend on the content. A 1 might just blow the fuse, a 0 will leave the content stay, right? So once you program it, you cannot go back, you cannot erase. So it's called a one-time programmable, right? This is for the PROM. So you can see that it's not so, sometimes when the chip is too expensive, you dare not to anyhow program it, because a single bit or single byte error, the whole chip has to throw away because you cannot reuse it, right? That's why I think it's not popular. This PROM itself is write once, not erasable. So subsequently they come out with the EE. Just now I talked about micro mouse, is more the EE PROM. EE stands for electrically erasable ROM. Okay, that means the chip will be able to reprogram many times. Something similar to your flash memory. Your flash memory will be able to rewrite many times, right? So this EEPROM also the same thing, except EEPROM is a lot slower than your flash memory, okay? These are things in the past, right, 10 or 20 years ago, and I just now mentioned that if you do a micro mouse project, most likely you will buy one of these, because you need to keep fine-tuning your program. Every time you change your program, you need to reprogram this EEPROM, so that the microcontroller will run a new version of your program. And in order to do this, you need to do it many times. And with a single EEPROM, you should be able to last many cycles, right? So this is the difference between the EEPROM and the PROM. PROM is once only, cannot reprogram, right? Right, that's about the ROM. And of course, just now I mentioned about flash memory. You all are lucky. With this generation, we do not talk about EEPROM, which is slow and very cumbersome, right? With the flash memory come into picture, nobody's talking about EEPROM, because the flash memory is similar, except it's having higher performance. In fact, most of the device today will have certain so-called flash memory built in, right? Your video recorder, sorry, not video recorder, your what do you call it, the video disc player, right? Normally we have certain flash memory inside, because they will ask you to upgrade. Sometimes they have a new version of their firmware. They will say you can actually program it, reprogram it to get a better performance, or to correct certain error, right? So most of the digital device will have certain firmware built in, stored inside the flash memory, and it allows user to reprogram it, right? And it's field programmable. That means you can do it on site. You don't have to bring back to the factory. Flash memory can be erased electronically and rewritten. So typically used for what? Store your data, basically your video, your audio, whatever thing you want to store, right? You have many copies of this flash memory. Right, a little bit, some of the technical terms related to memory. The first one, I talked about this access time many times, right? Access time is the amount of time it takes for the processor to read information, the bytes of information from the memory, right? Every time when you move a byte, how long it takes. And typically measured in what? Nanosecond. What is nanosecond? It's 1 billion of a second. That means 1 second divided by 1 billion, right? That's about the time it takes. So typically memory will take around from 5 to 70 nanoseconds. The 5 basically more for the SRAM, static RAM. The 70 more for the what? For DRAM, dynamic RAM. And just for a kind of feeling, because sometimes we talk about nanosecond. What is nanosecond? I mentioned in the previous lecture, the speed of light or electricity is what? 1 foot per nanosecond. That means during that 1 nanosecond, the electricity will travel about 1 foot, or light should be travel about 1 foot, right? And he said, how about the blinking of your eye? There's a measurement there. It's about 0.1 second. Okay, every time you blink, it takes about 0.1 second. So with that blink itself, the computer might be able to perform some 10 million operations. Okay, because that is about 100 million nanosecond. For 0.1 is 100 million nanosecond. Okay, that's a number. And with that number of nanosecond, remember the computer work very fast, right? So this is, when we talk about access time, we measure in nanosecond. Remember that? And that is for the memory. The other area that we'll talk about the access time will be the storage. That we are going to cover next week. When we talk about memory, we say it's a time it takes to store the storage. Sorry, it requires to move from memory to processor. Just now we mentioned, right? However, we also mentioned about access time for storage devices, right? It said time it takes for the storage device to locate items on the media itself. For storage devices, the access time is the time taken to locate a particular byte on the media itself, right? So we have this table here show you the relative speed. How fast can you get the data transfer, right? So we rank from faster to slower. The faster is the primary storage, which are they? The RAM, right? DRAM and SRAM, which is a lot faster. When it comes to secondary storage, hard disk is the fastest, followed by CD or DVD. And then also we have some other so-called miniature storage device, no more in use, the small hard disk, right? And then we have tape drive, followed by the floppy drive. So, and the last column here will show you, because of the access time, also the transfer speed, transfer rate, it is good for some usage, not for the others, right? In order to move instruction into the CPU, the data into the CPU, typically you need to have the memory, right? And for others, like long-term storage, you use other storages. So we look at the relative speed, the access time of a hard disk and RAM. For hard disk, we are talking about, in terms of milliseconds, 6 milliseconds, right? For DRAM or SRAM, we talk about nanosecond. So we talk about 60 nanosecond, 6 times 10 to the power of minus 8. If you compare the two, which will be 100k times, that means the RAM access time is 100,000 times faster than the hard disk. So if you want to move data from the RAM, it will be 100,000 times faster than the data you want to move from the hard disk. So just remember that. That's why we will normally copy the data or instruction from hard disk into the memory and sit there for a long time, right? Just now we also mentioned that the more memory, the faster the performance, right? So if you have more memory, you can move all the file into the memory, right? So that you can process it from the memory. And these are some other memory and storage terms. I think you can go through yourself. The way like how big is kilobyte, how big is megabyte. Okay, I think go through yourself the terms that you use to describe the memory size. Right, we shall stop here. Tomorrow we shall continue on expansion slot. See you tomorrow.